Welcome back. This is analog electronic circuits. This is lecture 26 and today we are going to talk about the common source, common gate, common drain circuits revisiting. Okay. So, in the last class we had looked at capacitance, exclusively capacitance in the MOSFET, and we saw that the MOSFET small signal model not only has GM, RDS, GMB. So, the MOSFET small signal model not only had these three components GM, RDS, right. So, we had GM, VGS, GMB, VBS, RDS. Okay, these were the three standard ones that we have been looking at from the beginning. And then because of capacitance, there are four more elements. I have got CGD. CGD is comprised of Cox, 1/3 of Cox at pinch off plus overlap, gate to drain overlap. So, 1/3 of Cox plus gate to drain overlap. CGS comprises of 2/3 of Cox at pinch off plus gate to source overlap. Now, at pinch off this is 2/3 of Cox, but beyond pinch off, well beyond pinch off, it becomes almost all of Cox, and CGD likewise becomes closer to 0, right, and you are left with only overlap for CGD. Then you have got CBS, and CBS comprises of junction capacitance between body and source, okay, and this is dependent on the bias voltages of the source and the body. So, body if body and source are at equal voltage, then you get only the zero bias depletion width. If source is at a higher voltage than the body, then the width becomes more, the depletion width becomes more, and therefore, the capacitance becomes less. So, the maximum capacitance over here is when it is 0 bias, right, when body voltage is equal to source voltage. And likewise, the drain to body capacitance is also there. This is also a junction capacitance, and this also depends on the drain voltage as well as the body voltage, drain to body bias voltage. Body is the lowest voltage in the NMOS, right. Drain is going to be a reasonably high voltage, assuming that you are in the flat region of the MOSFET, right. Is drain a high voltage or no? Drain is reasonably high. I mean V drain to source has to be more than VGS minus VT. So, drain is somewhat large, at least more than 0.2, 0.3, right. So, drain to body is reverse biased. If drain to body is reverse biased, then the drain with the junction capacitance is small or large? Small, because the depletion width is more, right. When you are reverse biasing, the depletion width is increasing, okay, that is the reverse bias, right. Depletion width increasing means it is harder for the carriers to come from this side to that side, right. So, that is why the depletion width is increasing when the reverse bias is increasing, that is how you remember. Now, if the depletion width is increasing, then the capacitance is going down, because the insulator is now bigger, okay, wider, thicker. All right. So, this is the idea. So, which of these is going to be larger, CDB or CSB? Let us call this CSB. Which is larger, CDB or CSB? CSB is larger, because source voltage is smaller than the drain voltage. So, source to body reverse bias is going to be less than drain to body reverse bias, right, and in that sense the capacitance is going to be more, right. So, CSB is going to be more than CDB, and similarly CGS is always going to be more than CGD, right, because the drain is at a higher potential than the source. Okay. So, most of Cox is going to come as part of CGS and not as part of CGD. Okay. So, this was the discussion that we had in the last class, and now we are going to build on this. We are going to use this small signal model to analyze our common source amplifier, the very first circuit that we studied, the common source amplifier. Then we will briefly study the common drain amplifier and then briefly study the common gate amplifier. Okay. All three we are going to study, and then we are also going to study the cascode after that. So, that is the agenda that is coming up. So, first we are going to look at the common source amplifier. So, by now you should be comfortable with the small signal analysis, right. I am not going to draw the biasing anymore, because the biasing can be done using a variety of techniques. It could have been biased with a current source, biased with voltage division, all kinds of things. It could be, this could be part of a differential amplifier. I do not know what is going on, right. This is the small signal circuit, okay, that I have drawn. I am not going to replace the MOSFET right away. In fact, I am not planning to replace the MOSFET at all, right. My strategy is that you should think about what is inside the MOSFET instead of wasting time drawing diagrams. Okay. Draw this core diagram, that is the MOSFET resistor small signal diagram, and then that is it, right. Do not bother doing more and more sketches and wasting time. Okay. So, we have this small signal circuit, and the way you ordinarily analyze this is with the help of Norton equivalent, right. How do you do the Norton equivalent? You measure the short circuit transconductance and you measure the output impedance. So, if I measure the output impedance first, let us connect V in to ground. Okay. V in, I imagine it is at ground. Automatically inside the MOSFET there was a GM times VGS, VGS is now 0. So, that GM has gone away. GMB times VBS, body is also at 0 anyway, source is at 0. So, that has also gone away. All that remains inside the MOSFET is RDS, which means that the output impedance looking in from the output is nothing but RD in parallel with RDS. So, I am just recollecting the DC analysis. All right. And the next thing that you do is you also find out the short circuit transconductance or the short circuit current. So, you apply a short circuit at the output node, apply your input and measure what is the current in the short circuit that is at the output node. So, I apply V in over here, okay. Output is shorted to ground, which means that the element RD, both sides of RD are at ground and therefore, no current can go through RD. Likewise, inside of the MOSFET there is RDS, both sides of RDS are at ground and therefore, no current can go through RDS. GMB anyway does not matter, because body is at ground, source is at ground. Okay. So, all that I have is GM, GM times V in is the current, right, and that current is forced to flow through the short circuit. So, the short circuit current coming inside is GM times V in, that is the current coming inside, and if you now think of the transconductance, that is just equal to GM, because the transconductance is the current divided by V in. So, V in cancels out, you have only GM. Okay. And if you are asked what is the voltage gain, the voltage gain is multiplication of the short circuit transconductance with the output impedance. Basically, it is a Thevenin to Norton transformation. All right. So, the voltage gain is GM times RD in parallel with RDS, but you have to take care of the sign over here. Okay. The sign is important, the current is coming in. So, the sign is going to be a minus. All right, that is how you remember, or if you do not want to remember it, just do a transformation from Thevenin to Norton equivalent. The Norton equivalent looks like this. You do not have to do anything, right. This is GM times V in, this is R out, right. You do not have to do any transformation also. You just have to imagine this, and therefore, the voltage over here is going to be minus GM V in R out, which means the voltage gain is minus GM R out. Okay, so, this is the overall plan of things. This is what happens without the capacitors. Now, let us throw in the capacitors. So, first of all, I have got CGD between the gate and the drain. I have got CGS between the gate and the source. I have got C drain to body, and body is at ground, and I have got C source to body, source is at ground, body is at ground. So, no current can go through C source to body, and therefore, I am not even going to draw it. Okay. All right, let me draw it just to make you happy. Here it is, see, source to body, body is at ground, source is at ground, and therefore, this one is irrelevant. Okay, it exists, but no current can go through it, it is irrelevant. Fine. So far so good. All right. Now, we are going to do the same two experiments, the short circuit transconductance and the output impedance, and instead of calling it R out, we are now going to call it Z out, okay, because it is now going to be an output impedance, that is all. Okay. So, let us first find the output impedance, and when I do the output impedance experiment, V in is going to be at ground, if V in is at ground, CGS has no current going through it, because both sides of CGS are at ground. All right. Likewise, inside the MOSFET, I have got GM and GMB, both are nulled out like last time, like in DC. So, inside the MOSFET, all that is there now is RDS, that is all that is there. Then I have got CDB, CGD and RD, and these are all between V out and ground. Between V out and ground I have got CGD, V out and ground I have got CDB, V out and ground I have got RD, V out and ground I have got RDS. And therefore, the output impedance is the parallel combination of RD, RDS, CGD, CDB. Fine. And do you know how to write the simplify this? No, I am sure you know how to simplify this given time. Given no time, can you simplify this? There is a trick. Okay. So, let us see what that trick is. It is a very nice trick. The trick is to understand that all of these okay, H of all right, let us do it slowly. let us not jump the gun over here, we will do it slowly. Okay. So, let us rewrite this as R D parallel R D S in parallel with this combination. Okay. And what is this combination? 1 by S C G D in parallel with 1 by S C D B, it is 2 capacitors in parallel, they add up. Okay. So, this is nothing but 1 by S C G D plus C D B, all right. And you can place these two in parallel, these two combinations in parallel, and you can do the crunching, the algebraic crunching, or what is easier is to do the following. This is the DC quantity, okay. So, it is R, that is the DC quantity, divided by 1 plus S C R. Okay. So, you can do the algebra, you will come up with this answer, do not you worry about it. All the format, always the format is going to be the DC quantity divided by 1 plus S tau, typically. This is going to be the typical format of things. If not, it is going to be like this, some DC quantity into 1 plus S tau Z by 1 plus S tau pole. Okay. If it does not even look like this, it is probably going to look like this. And so on and so forth. So, this is the template, this is how it is going to look like, the expression. So, you have the expression at DC, right. At AC, all of this is going to evaluate to a 1, because S is equal to 0. So, all these will evaluate to a 1, okay, the other quantities. This is going to evaluate to 1. At DC, this is going to disappear, all gone, right. So, at DC, it is just going to be whatever is on the top, whatever is the DC parameter. So, it is the DC stuff. All right, this is the template. This is how all the impedances, all the S parameter, all Laplace expressions are going to look like. You are going to have a DC quantity. Okay. So, there is a subtle difference between what you will find in control theory books and what you will find in analog circuits. Subtle difference. In control theory books, if you open any control theory book, they are going to write it in this fashion. Okay. Or let us not write it like this, S plus Z1 into S plus Z2 into S plus Z3 etcetera divided by S plus P1 into S plus P2 into S plus P3. This is what you will find in the control theory books. Okay. This whole thing times some random constant, some constant, okay, some scaling constant. This is how a transfer function is going to be written in a control theory book. Now, the same transfer function is going to be written in an analog circuit book in a slightly different way. Okay. The same transfer function, if you ask an analog circuits person to rewrite the same transfer function, then he is going to write it in this fashion. Okay. Why does the analog circuits guy like this format? Because the DC quantity is appearing outside. The scaling constant is not some random number, it is the DC quantity. So, if you plug in S equal to 0, all of these will evaluate to 1 and you will be ending up with just the DC quantity. So, we always like to write, we meaning analog circuits people, write their Laplace transfer functions in this format. This is the format for analog circuits. Okay. I do not know about the control theory people, why they like the other one, I really do not know, right. It is not important. This is an analog circuits course. We are going to stick to this as the format for our Laplace transfer functions. Okay. So, this is the format. We have abided by the format. Okay. It is always, this term is always going to be 1, fine. The constant is always going to be 1. When you are doing analog circuits, the constant term in the Laplace transfer function is going to be a 1, that is it. So, RD parallel RDS, this is the DC quantity divided by 1 plus S times a time constant, which is nothing but capacitance times resistance is time. All right, we all know that, and we all saw that the resistance here is RD in parallel with RDS. We saw that the capacitance here is CdB plus CGD. Therefore, the expression do not have to do anything, the expression is straight away the DC quantity divided by 1 plus the time S times the time constant, the time constant being R, RD parallel RDS times the combination of the capacitor CdB plus CGD. So, by inspection you can write it just like by inspection you had written this, the same way you can write this. Okay, you do not have to do this stuff at all. All right. Now, this is only one experiment so far. The next experiment is the short circuit current. So, this is the experiment, you are applying V in, you are going to measure the current over there, and the understanding is that inside the MOSFET RDS carries no current because both sides are at ground, GMB carries no current because body and source are at ground, right. So, all that is there inside the MOSFET is 1 GM, and outside the MOSFET RD carries no current because both sides are at ground. C source to body was always irrelevant because both sides were ground, source and body. C drain to body is also irrelevant because both sides are at ground and it does not carry any current. Drain is at ground, body is at ground. The only other thing you have is C gate to drain, which is carrying a well defined amount of current. This side is V in, the other side is ground, and you have CGS and it is carrying a well defined current, but that current has no relationship with this short circuit current, it is not really affecting it, it is just going over here. Okay. So, yes, there is current through CGS, but it does not matter. So, all that I have over here is CGD, and therefore, the current that I have drawn over here is nothing but Gm times V in. Okay. That is the current going down through the MOSFET is Gm times V in, but there is additional current coming in over here, which is V in times SCGD. And there is a minus sign over here. Beware, be very careful, check, double check the sign. What I have written is correct. This current is V in times SCGD. The current over here is Gm times V in. All right. And therefore, this combination current is going to be Gm V in minus V in times SCGD. Check and double check this. Why? Is because in circuits normally these minus signs do not come inside expressions. Okay. So, this is an anomaly, this is not something that happens on a routine basis. Okay. This minus sign usually triggers a warning, it should trigger a warning saying that maybe something is wrong, let me recheck, and you have to recheck over here, and indeed in this particular case the minus sign happens to be correct. So, the overall transconductance is Gm minus SCGD, this is the transconductance, and as I said before, we do not like writing it like this. Okay. We like writing it as the DC quantity times 1, in this case minus SCGD by Gm. Okay. And clearly this is a pole or a 0? This is a 0, yes, this is a 0, and this 0 is in the left half plane or in the right half plane? This is in the left half plane. This 0, I am sorry, yes, this is a right half plane 0. Okay. This 0 is a positive 0, it is in the right half plane, and this also does not normally occur. So, normally under when things are all nice and on regular circuits, right, you will not see zeros coming in the right half plane. If at all a 0 comes, it will be a left half plane 0. This is a special circuit, okay. It is a common source amplifier, it is a special amplifier. Okay. It happens to be your favorite amplifier, but that does not mean that it is not special. It is a special circuit, that is why you are getting a right half plane 0 over here. Fine. So, what is the overall V out by V in? Laplace transform is going to be minus transconductance times output impedance. So, minus Gm is the DC quantity, Rd parallel Rds was the DC output impedance, times the poles and the zeros, 1 minus SCGD by Gm, that is coming from the transconductance, and coming from the output impedance is 1 plus S C gate to drain. At the output node you had gate to drain capacitance as well as drain to body capacitance, and Rd parallel Rds. Okay. So, this is the overall transfer function. There is a right half plane 0 and there is a pole. The pole is at the RC of the output node. Okay. The right half plane 0 comes because of CGD. Fine. This analysis is clean, there is no problem. So, when you analyze like this, you will not have any problem. Usually your analysis is going to be correct, right. There are, however, some shortcuts to do the analysis. This analysis is okay, it was quite fast, right. Do you really need a shortcut? I don't see the need for a shortcut in this particular situation. Okay, we don't need a shortcut. Let us not worry about the shortcut. There are some, people have come up with some shortcuts and the shortcuts obfuscate things a lot, and they are also not accurate. You will not end up with this answer when you apply those shortcuts. You will end up with something else, and then it is going to be very hard to justify the shortcut and so on and so forth. So, let us not bother with any shortcut. This analysis was quite fast so far, right. All we did, we are also trying to learn. So, let us also learn how to do the correct analysis in one shot. Okay. This is the correct analysis in one shot. Find output impedance, find short circuit transconductance, you are done. Okay. You have found the overall transfer function. Any questions so far? So, this is the analysis of our common source amplifier. You can of course draw a pole 0 plot over here, a Bode plot for this, right. Should I remind you how to draw a Bode plot? Bode plot had a gain plot and a phase plot. Okay. See, Bode plot is nothing but a plot of this, okay, replacing S with j omega. So, I replace S with j omega and I sweep omega and I plot this quantity. Now, when you try to plot this quantity, you are trying to plot a complex number, right. So, it is very hard trying to plot a complex number. You can plot real part and imaginary part, but it does not make much sense to a lot of people plotting real and imaginary part. Instead, as engineers, what we do is we plot the magnitude and the phase. Okay. So, when you are doing the Bode plot, you always need two plots, one of the magnitude, one of the phase, because it is a plot of this complex number, this complex quantity with omega as the variable. Alright. So, this is going to be a magnitude plot, this is going to be a phase plot. Now, what this gentleman Bode was one of the last great engineers. Okay. He is actually a fantastic engineer from Bell Labs in the late 1930s. Okay. And there are a lot of contributions that came from Bode. The circuit design community is indebted to Bode in many ways. Okay. So, this Bode plot has come from him, and what he figured out is that instead of plotting just the complex number, if we plot the log of the complex number, it might make sense more, and at the same time it might be easier to plot. Okay. So, two things in one shot. First is it will make even more sense. Why will it make even more sense? Because the ear hears in decibels, right. You can hear a mosquito flying next to your ear when you are sleeping. You can also hear loud fireworks right next to you. Okay. So, the ear has a huge dynamic range, right, and the sensitivity of the ear is in the log scale. In a lot of places the log scale becomes very important. For example, in vibrations, when you measure an earthquake, you measure in the Richter scale, which is nothing but a log scale. Okay. So, a lot of places, a lot of effects come out, you appreciate when you talk about that effect in the log scale. So, sound is one, sound is a kind of vibration, all vibrations, right. They you see, you appreciate the effect of the vibration more in the log scale. Okay. So, likewise all communications, right, electric field, magnetic field, all of these, when you look at them, when you appreciate them in the log scale, the appreciation happens is more. So, this is what Bode figured out, that people will appreciate the graph more if instead of plotting just the complex number, I plot the log of that complex number. And then the next thing that he figured out was that not only will people appreciate it more, it is also easier to plot. Okay. So, this is how. So, this is just a refresher of your Bode plot. This is not really material for this course. So, the y axis is going to be log of the magnitude. Let us just do a little bit of brief analysis over here. If I have a complex number, let us call it h e power j phi. Okay. If I take log of this, then it is going to be equal to log of h plus nothing but j phi. Fine. So, this quantity is the phase j times phi. You do not have to plot the j part of it, you just plot phi. And in the other plot, you are going to show the log of the magnitude. So, in one case you are going to show log of the magnitude, in the other case you are going to show the phase phi. Now, the log of the magnitude, the decibel scale is actually 20 times log of the magnitude. So, instead of plotting just the log of the magnitude, you can plot 20 times the log of the magnitude, and that is the decibel scale. So, what does that mean? So, every 20 decibels is actually a factor of 10. Okay. So, that is the decibel scale, that every step of 20 decibels is a factor of 10. Oh, by the way, this is when we are trying to plot something which has which is a ratio of two voltages, a ratio of two currents, okay, a ratio of two electric fields, a ratio of two magnetic fields, all right, a ratio of two vibration amplitudes. Then you are going to use 20 times log to the base 10. Okay, that is a decibel. However, when you are trying to express, when you are trying to plot the ratio of two powers, the power can be because of electricity, in which case it is going to be voltage squared by R, or it will be I squared by R, or it is going to be so everywhere it is going to involve a square term. Okay. So, either voltage squared ratios, I squared ratios, or amplitude square ratios, electric field square ratios, magnetic field square ratios, right, vibration amplitude square ratios, all right. So, in all of these cases you will find that there is a square term coming in whenever you are trying to look at power as opposed to the amplitude, right. In such a situation, when you convert it to decibels, when you convert this ratio to decibels, you have to use 10 times log, because the square is going to come out of the log and it is going to make the 10 a 20. It is going to make it 2 times and it is going to become 20. Okay. So, ratio of powers is always 10 log, ratio of amplitudes is always 20 log. Okay. And if it is not a ratio, it does not come into the dB scale at all. This is a ratio of two voltages, okay, two amplitudes, in which case it is going to be 20 log, 20 log to the base 10. That is the idea. Okay. So, this is one part, the y axis is one part of the Bode plot, one feature. Now, what is interesting is that the x axis also has to be a log scale. What is the x axis, by the way? Omega, right. Remember, we replaced s with j omega and said let us plot it as a function of omega. That was the entire objective. So, the x axis has to be omega, but in case of the Bode plot, we are going to plot omega in the log scale, which means that if this is 1 radian per second, I am going to call this 10 radians per second, 100 radians per second, 1000, 10,000, 100,000, no. Okay. So, in the Bode plot, every step is a factor. Okay. It can be a decade like I have drawn, it could be a step of 2, that is called an octave, all right. And there is something nice about these octaves and decades and so on, and that is what comes out in the Bode plot, all right. So, this is the magnitude plot. Then likewise, the phase plot is going to happen on the bottom side. Now, why does the phase come on the bottom side? Because normally it is very hard to find a system which has phase more than 0 degrees, because that kind of a system would be non-causal. Okay. Usually your system is going to be a causal system, which means that the output is going to be delayed from the input in terms of time, and that usually means that the phase is going to be negative. It's always, output is always going to lag the input, right. It is very unlikely that the output is suddenly going to start leading the input. Even in such a situation, you are going to draw it as minus 200, 359 degrees, you are not going to show it as plus 1 degree. Okay. When output is leading the input, you are going to draw it as minus 359 degrees, not as plus 1 degree, because plus 1 degree appears as if the output knows what the input was, input is going to be in future. Okay. So, that is why we always draw this in the bottom half on the negative scale, all right. There is no reason for the phase to be more than 0 degrees, plain and simple. Okay. Now, this is the setup for the Bode plot, and this log of h plus j phi has to be plotted in this, right. Now, it so happens that it is very easy to plot. I will not show the mathematics right now, but all I am going to tell you is that you locate the pole, right. First of all, you need to understand that DC on this axis, DC is outside the page. This is not DC, this is only 0.1, next 0.01, 0.001, you can keep going, right. DC happens at minus infinity. Okay, that is something to appreciate. This is the log scale, DC is far away, all right. So, whatever is at DC, that continues, okay, that value continues till the frequency starts playing an effect. Okay. So, if your DC value is 40 dB, there you are. It is a straight line till frequencies, the capacitors start playing a role, till the pole or the 0 starts playing a role. Okay. Now, what is going to happen at the pole is nothing much. The slope of this curve is going to change by minus 20 dB per decade. That is all that happens at a pole, and all that happens at a 0. So, this is a refresher for the Bode plot, right. So, I am not going to discuss the maths why it happens. It is actually very easy to see why it happens. You just plot out log of h and you will figure it out. But what we are going to do is, we are only going to say right now that at the first pole the slope of this axis, this graph changes by minus 20 dB per decade. At a 0, the slope of this line changes by plus 20 dB per decade. What does decade mean? Decade is this unit size, factor of 10. Okay. So, if the slope changes by 20 dB, let us say your pole is at 1 kilohertz. So, it is flat, so not 1 kilohertz, 1 kiloradian per second. Okay, it is flat till 1 kiloradian per second. At 1 kiloradian per second, the slope of this changes by minus 20 dB per decade, and minus 20 dB per decade on this graph looks like this. Okay. So, this is 20 dB, this is 20 dB, and this grid side is 1 decade over here. So, from a slope of 0 I went to a slope of minus 20 dB per decade. If another pole comes, then it is going to, the slope is going to decrease to minus 40 dB per decade, and so on and so forth. Now, a 0 comes, right. So, our transfer function has a pole and also a 0. Which of these is going to come first? The pole is going to come first, because this time constant is much larger than the other one. This is CGD plus CDB. Okay. So, this capacitance is certainly larger than CGD, and 1 by Gm is a small resistance compared to RD parallel RDS, okay, which means this is large, this is large. Okay. This time constant is much larger, which means in frequency it is a smaller frequency. So, this pole frequency is smaller than the 0 frequency. So, the pole arrives first, and then sooner or later the 0 comes, and when the 0 comes, the slope increases by 20 dB per decade. All right. Now, when you are doing these log plots and so on, things are not going to be such piecewise linear, solid straight lines. Okay. This is going to be some smooth curve, right. So, all you now have to do is, you have to make this curve appear smooth and you are done. So, at the corners you have to cut a little bit, and the amount to cut is also there. You have to cut by 3 dBs at the corners, right. All of this is part of the Bode plot theory, right, how much to cut the corners by. So, you have to cut the corners and then smoothen the line by 3 dB. All right. Next, we also have to plot the phase, and the phase plot also happens to be something very easy. At DC, the phase is going to be 0. Okay. So, we are not going to worry about DC. You are going to always start from DC, which is at phase 0, and then at the first pole, after the first pole, you are going to get a phase adjustment by minus 90 degrees. At every pole, the phase is going to drop by 90 degrees. All right, this is the idea. Every pole comes, one pole 90 degrees, another pole another 90 degrees. So, if a pole arrives, then you are going to get a phase delay of 90 degrees, phase lag of 90 degrees. All right. And again you have to make it a little smooth, right. It is going to pass through minus 45 degrees at that precise point, and how much to smooth by and so on, all of these are plus minus 1 decade, you have to smooth it by plus minus 1 decade around the pole. Okay. So, this is the idea. Now, what happens at a 0? Just like in case of a pole, the phase goes down by 90 degrees. Ordinarily, in case of a 0, the phase is going to go up by 90 degrees. The only problem is we are not in an ordinary situation. We have a right half plane 0, and in a right half plane 0, phase goes down by 90 degrees. Okay. Ordinarily, phase goes up by 90 degrees, it is opposite of the pole, but in a right half plane 0, phase also goes down by 90 degrees, just like a pole. So, this is our Bode plot. Okay. Once again, at this precise point at the 0 frequency, I have made an adjustment of only 45 degrees, okay, not the full 90. The full 90 spreads around over a decade. All right. So, this is how you draw the Bode plot. The principle of drawing the Bode plot remains the same, right, whatever transfer function you are trying to plot. This 40 dB comes from the DC part, right, GM RD parallel RDS, that gives you this number, right. Then the pole frequency is 1 by the time constant, the 0 frequency is 1 by this time constant. Okay. So, all right. So, we could not accomplish what we planned to do. We had planned to do common source, common drain, common gate, right. Unfortunately, all we have done is just the common source, but that is okay, because we also spent some time looking at how to plot. We spent some time with how to what is the template transfer function and so on and so forth. It took a little time. The first the first time you do it, it takes a little time. The next few circuits are going to be much faster and easier. All right. So, let us stop here and we will continue again. Thank you.